Hello, in this video, we'll be looking at lesson 11.4 on inscribed angles. The essential questions that we'll answer are how do you find the measure of an inscribed angle, and how do you use inscribed angles and their properties to solve problems. Let's start by defining the term inscribed angle. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. Notice in this diagram over here that the vertex of angle DEF, that's point E, is on the circle, on the edge of the circle, which makes angle DEF an inscribed angle. Also notice that ED and EF are both chords. Now, an inscribed angle also creates an intercepted arc. We talked about intercepted arcs earlier in lesson 11.2 when we looked at the central angle intercepting an arc. Well, inscribed angles also have intercepted arcs. Intercepted arcs are an arc whose endpoints lie on the side of an inscribed angle, and all of the points on the circle between them. Here, the arc DF is the intercepted arc to the inscribed angle, angle DEF. And then our final term here is the word subtends. And a chord or arc subtends an angle if its endpoints lie on the sides of an angle. Notice that in this picture, the endpoints of arc DF, point D and point F, lie on the sides of angle DEF, which means arc DF subtends angle DEF. So there's our arc, and DEF is the inscribed angle. There's a relationship between the measure of an inscribed angle and the measure of its intercepted arc. The measure of an inscribed angle will always be half the measure of its intercepted arc. In our diagram here, there are three different cases just depending on where the inscribed angle is located. It really doesn't matter as long as it's an inscribed angle, meaning the vertex is on the edge of the circle. For any inscribed angle, the measure of that inscribed angle, which in our diagram is angle ABC, is equal to 1/2 the measure of its intercepted arc, which here would be arc AC. As an example, suppose that we know in this first case that arc AC is 80 degrees. Using this theorem, we would be able to say that angle ABC is 1/2 of 80, which is 40 degrees. But this theorem can also work in reverse. You can use the measure of the inscribed angle to get the measure of its intercepted arc. All we have to do is multiply the equation by 2. So imagine we multiply each side by 2, and when you multiply 1/2 by 2, it disappears. So it's just going to be the measure of arc AC is equal to twice, so 2 times the measure of the inscribed angle, angle ABC. As an example, suppose in case 2 that we knew the inscribed angle was 30 degrees. If we know the inscribed angle, we can just double that 2 times 30 to determine that the intercepted arc, arc AC, would be 60 degrees. There's a corollary to this theorem as well, and the corollary states that if inscribed angles of a circle intercept the same arc or are subtended by the same chord or arc, then the angles are congruent. And in our picture here, you can see that there are 3 different angles. Angle ACB here in red intercepts arc AB. Angle ADB in blue intercepts arc AB. And angle AEB right here also intercepts arc AB. Since each of those 3 angles intercept the same arc, you can see that arc AB right here in orange is intercepted by all three of those angles, we would be able to state that all three of those angles are congruent. Let's try an example now where we find the measures of arcs and inscribed angles. In this first picture, we're going to start by finding the measure of the inscribed angle RST, which I just outlined in purple. Notice that RST is an inscribed angle, and using the theorem that we just filled in, the inscribed angle is half the measure of its intercepted arc, which here is arc RT. Notice that arc RT is 120 degrees, while half of 120 divided by 2, would be 60 degrees. This next one is a typo. Go ahead and change that to the measure of arc SU. And the measure of arc SU is this arc right here. Notice that that arc is created by this angle right here, which is 40 degrees. We know that the arc is twice the measure of the inscribed angle, meaning arc SU is 2 times the measure of angle SRU. That's 2 times 40, which is 80 degrees. Here's a try now problem for you to try on your own. Please pause the video now, and then when you hit play again, the solution will be posted. Here is your solution for angle PRU. We take 118 and we divide it by 2 to get 59 degrees for the inscribed angle. And then for the arc SP, the arc is going to be twice the measure of the inscribed angle, and 2 times 27 is 54 degrees. Next, we're going to talk about polygons that are inscribed in a circle. For our first theorem here, an inscribed angle subtends a semicircle if and only if, which we know means it works both directions, the angle is a right angle. Let's mark up our picture a little bit. An inscribed angle subtends a semicircle. Notice that arc AB right here is formed by the diameter segment AB, which means we have a semicircle right here. Recall that a semicircle, half a circle, is 180 degrees. And well, if the inscribed angle is half the measure of the intercepted arc, well, 180 divided by 2 is 90 degrees. The second theorem has to do with an inscribed quadrilateral. Remember that quadrilaterals are polygons with exactly 4 sides. And if a quadrilateral is inscribed in a circle, then its opposite angles will always be supplementary, meaning they add to 180 degrees. Let's look at why that's the case. Suppose in this picture, we look at angle A right here and angle C right there. Notice that angle A, if I look at that angle, it creates this arc right here, arc BD. Similarly, angle BCD creates this arc. Notice that the two arcs together, the blue one and the red one, really just make the full circle. And a full circle is 360 degrees. The inscribed angle will always be half the arc. So that means that they have to add to half of 360, 180. And if we could fill in just a little note over here in our quadrilateral, both pairs of opposite angles are supplementary, meaning the measure of angle A plus the measure of angle C is equal to 180 degrees. And also the other set of opposite angles, the measure of angle B plus the measure of angle D, is also 180 degrees. Let's try a few examples. Here we're going to start by finding measures in inscribed triangles. The first one, we have an inscribed triangle, and notice in this triangle, the triangle subtends a semicircle. Arc TR is a semicircle, and that tells us by the theorem that we just filled out that angle RQT is a right angle, meaning its measure must be equal to 90 degrees. Well, notice in the diagram that the measure of angle RQT is 4x plus 6. So 4x plus 6 has to equal 90. And from here, you can just do your algebra. Subtract 6 on each side to get 4x equals 84. We'll divide by 4 and get x equals 21. Now, this next problem isn't actually an inscribed triangle. It is one of the theorems that we talked about toward the beginning of this lesson. Notice that there are two angles that are marked with variable expressions in the diagram. We have angle ADC that we're trying to find right here. I just made angle ADC green. And then the other angle that we are given is angle ABC. Notice that both of these angles create the same intercepted arc. Arc AC is intercepted by both. Since both inscribed angles intercept the same arc, arc AC, we know that the angles are congruent. And we can use that to set up an equation. Angle ABC, you can see, is 10y minus 28. And that has to equal angle ADC, which is 7y minus 1. From here, we can do our algebra steps. I'm going to subtract 7y on each side. And I'm also going to add 28 to each side. We'll do kind of two steps in one here. 10y minus 7 is 3y. That cancels. And negative 1 plus 28 is 27. Well, a quick divide by 3 gives us our y value of 9. The question, though, doesn't ask us to find y. It asks us to find the measure of angle ADC. Now that we know y, to get the measure of angle ADC, we can just plug it in. So 7 times 9 minus 1, 63 minus 1 would be 62 degrees. Therefore, to answer the question, the measure of angle ADC is 62 degrees. Here's one final example type for this lesson. Notice that PQRS is an inscribed quadrilateral. It's an inscribed polygon that has 4 sides, making it a quadrilateral. Well, in an inscribed quadrilateral, remember that opposite angles are supplementary. There are 2 sets of opposite angles in the picture here, angle P and angle R. And then the other set of opposite angles would be angle Q and angle S. Now, we want to look at the opposite angles where we have expressions for both of them. So I don't want to use Q and S because we don't have an expression for S. But if we choose P and R, that will help us out. Remember that opposite angles are supplementary, meaning the measure of angle P plus the measure of angle R has to be 180 degrees. We can do our substitution here, 6y plus 1 plus 10y plus 19 equals 180. Remember to combine your like terms. On this side, 6y plus 10y is 16y. And then 1 plus 19 is 20. And now we are getting close here. Let's move that 20 to the other side by subtracting 20. And then we'll divide by 16 to get y equals 10. Now that we know what y is, we need to find the measure of each of the 4 angles in our quadrilateral. I'm going to start off with the measure of angle P. And angle P, you can see, is 6y plus 1. That's 6 times 10, add 1, 61 degrees. And then I'm going to do the measure of angle R next, just to verify that it adds to 180 with angle P. Plugging it in, we have 10 times 10 plus 19. That's 119 degrees. Notice that these two right here total to 180. They are supplementary. Opposite angles of an inscribed quadrilateral are always supplementary. Now let's try angle Q. Notice that angle Q is equal to y squared plus 48. Y squared would be 10 squared plus 48. Well, that's 148. For angle S, we know that together, Q and S have to total 180 degrees. Let's just take 180 minus the 148, and that will give us the value 32. The final example here is a try now. We have another inscribed quadrilateral. You're going to begin by setting up an equation to solve for b, and then once you have a b value, you're going to figure out the measure of each of the 4 angles in that inscribed quadrilateral. Please pause your video now and give this one a try. Here's your solution. Notice that I took the 2 opposite angles with the variable expressions here, and I added them together to equal 180, did my algebra, and ended up with b equal 15. Once we know what b is, we can find the measure of j, k, and g, and then we can use the fact that k and h are opposite angles in the quadrilateral to find angle h. And I have all of my work shown over here and all of my final answers in this box. This concludes lesson 11.4. Thanks for watching, and good luck as you practice some problems involving inscribed angles. Bye.